as we've been saying, this section of notes that we're doing in calculus, this unit that we're doing, is kind of the application of everything you've learned so far. And I know I've said this before, but in the past, when you've taken tests, and especially word problems, there's always this extra information that's out there that kind of trips you up. But I will be honest that it's pretty rare to see a question at this level where the information that they give you is just not pertinent. Most of it will help you along the way and will give you some kind of clue as to how to approach this question. Here we have a 10-foot ladder that leans against a wall. It says if the top of the ladder is sliding down the wall at the rate of 3 feet per second, at the instant the top of the ladder is 6 feet off the ground, how fast is the bottom of the ladder sliding away from the wall? Now, something that we have to remember or need to understand is that we are looking at a ladder that's leaning against a wall, right? So here's my ladder. It is sliding, so it's dropping down, and as that's dropping down, the bottom of this ladder is going to be kicking out. Now, just to give ourselves some variables here, let's think about this. It's best to express this up and down side as y, and this base here as x. Pretty easy, right? We know this is a 10-foot ladder. Now, does this shape or this picture remind you of something? My hope is that you think about, oh, that's actually like the Pythagorean Theorem. But you don't have two of the sides, right? So we'll get there in a minute, but I want you to think about, oh, Pythagorean Theorem, and this will be useful throughout, honestly, this entire unit. So we have this concept of x squared plus y squared equals 10 squared. And so what we do know, if we keep reading this over and over, we recognize that we have some other information besides a 10-foot ladder. We have this number 3, which represents 3 feet per second. In other words, the ladder is sliding down the wall. Now, when you see a rate like that, the way that we know, first of all, it's a rate is because it's per something, per second in this case, in terms of time. Now, this measurement, it's talking about it's sliding down the wall. So that is our y value, and it's in terms of time. The rates that we've been talking about, and we expressed this a couple days ago when we were putting things in terms of time, doing the derivative with respect to time, that expressions such as dy dt is basically saying the rate that y is changing in terms of time. So this is the rate y is changing in respect to time. And if I was to change that to an x, then again, you would recognize that that instead was saying rate of x, right? Changing in respect to time. So right now that 3 represents dy dt. And then it says, at the instant that the top of the ladder is 6 feet off the ground. In other words, this is when y equals 6. Okay, so you're like, well, what about x? What information do we have about x? Well, let's continue on to read the question. It says, how fast is the bottom of the ladder? So the fast is a rate, right? And so it's really asking for dx dt. It wants the rate that it's sliding out. And you might say, well, what's x? Can you find x? My hope is you could say, obviously, yes, because we have Pythagorean Theorem. All right, so let's find x. To find x, that would mean we have x squared plus 6 squared equals 10 squared. And of course, that's x squared plus 36 equals 100. And so we would subtract and get 64. And so x would equal plus or minus 8. And of course, we only need the positive value, right? And so we have 8 feet. So when y is 6, the x is 8. All right, so now how is that going to help you find dx dt? Well, this is where the implicit differentiation, as well as your knowledge of respect to time, is all going to play in. So what we're going to do is we're going to start back with that equation, x squared plus y squared equals 10 squared, and I'm going to do the derivative in respect to time. And so what happens here, all right, is I have 2x, but it's in respect to time, so this would be dx dt, plus 2y dy dt equals the derivative of 100. Yep, is 0. So now let's fill in the information that we know. We know that x is 8. We do not know what dx dt is. That's what we're trying to figure out. We know that y is 6, and we know dy dt is 3. And so from there, we have 36. I'm going to just bring that to the other side, making that negative 36, and I'm going to divide by 16 to get dx dt. Obviously, we can simplify that to be negative 9 over 4. And so that would basically say that our rate is negative 9/4 feet per second, that it is sliding away from the wall. Let's try another question. Let's look at this next one, a conical pile. We have a conical pile, or rather a sand falling from a chute, forms a conical pile whose height is always equal to 3 times the radius of the base. How fast is the volume increasing when the radius of the base is 3 feet and increasing at the rate of 4 inches per minute? Okay, so we have some information here, and let's just kind of go right after this. The first thing I'm looking at is the fact that the height is always equal to 3 times the radius. So height equals 3 times the radius. That's going to be important. How fast is the volume increasing? So that's the question, dV dt. That's what it's asking for. That's what it wants to know. And it says when the radius of the base is 3 feet. So I know that the radius is 3 feet. And I also know that it is increasing, the radius is increasing, so dr dt is increasing at a rate of 4 inches per minute. Again, notice that says inches per minute, and so there is a trick to that, because we wouldn't want this to be in feet, the radius to be in feet, and yet the rate to be in inches. So we would convert this pretty quickly, at least I hope you recognize, to 36 inches. Now, a formula that I would like to make sure that you understand, they do tend to give these to you, but just in case, you should recognize how to do this. If I want the volume of a cone, they did say this is a cone, right? So let's think about a cone. The base of a cone is a circle. So here's how I remember always to do volume formulas. We know the area of a circle is pi r squared, right? Whenever we do volume, we basically do, like length times width, and we do the times the height. The length times width is the area part. It's always area times the height. That's the volume, right? That's how you do volume for anything. Well, let's think about this. The height of this, okay, h, that's what that would be. Now, that would be if we were talking about a cylinder, but this is a cone. And so with the cone, if you think about that in respect to a cylinder, right, there's our cylinder, it's 1/3. We're taking off 2 pieces that it's not there. It's 1/3 that piece. So volume of a cone is 1/3 pi r squared h, okay? But as we found in our word problem, the fact is that we have actually 1/3 pi r squared, and in place of h, we're going to put r. So really, we have 1/3 pi 3r cubed, and the 3's would divide out, so we have simplified this to be pi r cubed. Any questions about that? Please make sure you note them. Hopefully you can see how I derived that equation. Now, so it's in terms of radius, yes, and we want to do the derivative of the volume because we want the rate in terms of time, how much that's changing. So the derivative of this whole thing, d dt, right, in respect to time would be dv dt. And remember, pi is a number. So that would be 3 pi r squared dr dt. And now we're going to use that to solve for the rest of this, what information we have. We don't know dv dt, but we do know that our radius is 36. And we do know that our rate is 4 inches, okay? Another way that this could have been approached, since we don't like huge numbers, would be instead leave this as 3 feet and say that this is 1/3 of a foot. And since I'm looking at that thinking, that would be a little bit nicer to solve, let me just show you what I mean. So instead of putting in 36, we would keep the 3 for the radius, and we would just put 1/3 for that rate of the radius because it just makes the numbers a little bit smaller. So that gives me 9 times 3, or 27, right? Divided by this 3 gives me 9 pi. So dV dt would be 9 pi feet cubed per minute. That's how the volume of this conical pile is changing, or rather increasing. If it said decreasing, we would probably put a negative on there to show by signage that it's actually negative. Okay? Now, in number 14, I want to just make sure that if you're doing number 14 tonight, it's important to note that for number 14, the relationship for the height is height equals 2 times the radius. And so hopefully that would help you to be able to answer that for 14. I don't know if I remembered to tell you that in class, so if not, just so you're aware, number 14, you might need that piece of information.